Hello everyone and welcome. Welcome back to SID3020 Natural Products and Biotechnological Processes. Last week we looked at some reaction, enzymatic reaction. So for today we're going to look at enzymatic enzyme kinetics in a little bit more detail, and hopefully by learning this you can actually see what's the importance of knowing the enzyme kinetics, the rate of the reaction in terms of producing the products that you want. Okay, so we've looked at this slide from the previous lecture. So it is basically enzymatic kinetics, enzyme catalyst reaction, a plot of enzyme catalyzed reaction. But what is wrong in this plot is actually reaction versus velocity. So this is actually wrong. It's actually plot of reaction versus substrate. Okay. So I just noticed this. Apologize for that. So that's why you can get V versus S. Okay, so V is the reaction velocity and S is the substrate concentration. Now, so I probably put it there as well. So substrate concentration. Now, as I also explained that in the reaction kinetics, in any reaction where it is biocatalyzed, you can actually get a V max. Okay, so a V maximum, which is the rate velocity of a maximum per reaction. So over here we've looked at a slope like that, where this is the concentration of product formation. Okay, and over time, of course, but for this one we are not looking at over time just yet. Okay, it's just looking at the reaction velocity, even though of course velocity is over time. But this graph actually plots a different concentration of substrate and how the reaction velocity will look like. As we reach a Vmax here for industrial purposes, we know that at one point Vmax will, okay, so that is not what we want, because if Vmax can only be achieved after say 24 hours or 48 hours, it is less, it is not what industry wants to achieve. Okay, because towards the end of the day Vmax might be important for a researcher, but for all industrial purposes, what you want is a constant production of a product. Okay, so at the end of time, for industrial purposes, normally you're not looking for Vmax. You want to know what Vmax is, but during application you don't want to reach Vmax, because if you reach Vmax, meaning that your enzyme is already saturated, there might be some other issues that might come into play, and therefore affecting all your product formation. So in an industry where you have an equilibrium like this, what you want is, going back into Lecher's principles, is that you want to constantly have a lot of product formed, correct? And based on the equilibrium principles, what you want is therefore to always take out your products from your equilibrium reaction, because once you take it out, the reaction will move towards one direction, correct? Okay, now that is not the only thing that the industry will do. So one thing is you want to constantly taking out your product, but at the same time you want to constantly adding in more substrate. Okay, so this will definitely push towards the product formation, and therefore you can maximize the products or whatever you want, and finally profit. Okay, now we're gonna look at a little bit on basic on enzyme kinetics, and to try and understand how you can actually do that. So the things that you need to remember, because I mentioned that you are not interested in Vmax per se, so you want to see something else. You want to see what's more critical is what is the rate of your product formation, right? Because when you constantly putting in your substrate and at the same time extracting out your product, so you want to have the best rate of reaction possible, right? Can you understand what I mean? Okay, because you want your product to be formed as quickly as possible, so that's the rate. But at the same time, you don't want the reaction to reach the maximum velocity, because if it reaches velocity, then it reaches plateau. So what you normally look at is the initial velocity, where you can relate this to the rate of reaction of the enzyme. So the faster the V naught, okay, so the lower the higher the V naught, means that the faster your enzyme are actually producing the product. So that is more important rather than the Vmax. Okay, but towards the end of the day, you can actually know Vmax and whatnot, but the basic principle is you want to know the rate of the enzyme producing the product. Now, the rate of product formation. Okay, so if you consider the steady state condition, whereby the reaction is in equilibrium, that's one thing. Okay, and steady state meaning that there's no change in thermodynamics, meaning that the temperature is constant and everything else is kind of like constant. There's not much variables. So the rate of production can be written as K and P. Okay, K is the equilibrium constant times the product concentration. So that is the rate of formation. Okay, so in steady state condition, the rates of change of enzymes. Okay, so this is where we're looking at the kinetics in more detail, and therefore you need to understand the basic principle of the rate of change. Okay, so rate of change, or sometimes you can do a triangle and put it rate. Okay, so rate of change, the delta sign or triangle sign means change of rate for the enzymes. Okay, so change of rate of the enzyme, because as you can see, right, so the enzyme originally is just the enzyme, now producing the enzyme substrate complex. So you can actually say that the free enzyme in the system are now converted to not a free enzyme anymore, because it's a bound, or it's forming a complex with the substrate. And then once, okay, so you need to consider, so what you say here is the loss of the enzyme. So when you consider the rate of change of just the enzyme, so we're not going to talk about E and S, because the enzyme substrate complex, there's another rate of change. Okay, so individually you can have the rate of change of E, you can have the rate of change of S, you can have the rate of change of your ES complexes, and finally you can have the rate of change of P. Okay, why do you consider this? Well, because as I said, this is the catalyst, so the rate of change of the component are similar, so you can actually combine it. That's why if you look at here, okay, so this paragraph, or this section of the reaction actually tells you about the rate of change in terms of loss. Okay, the rate of loss of the enzyme concentration minus the rate of okay, before that I'm gonna scrap that one. Okay, okay, so when you consider, so I actually not doing a rate of loss, so this one is we'll just put it there as K1. Okay, so constant for the formation of ES, or vice versa for if it move to one direction. If it move to the other direction, you consider it as K minus 1. Okay, because the rate is opposite, and it has its own value, okay, based on the concentration of ES. Again, because when you consider the rate, is you consider the where the arrow is moving, okay, so over where the arrow is going backwards. So to say this one is on the right, this one is on the left, based on the where the arrow is moving. So again, this is the basic, if you can't remember. So the rate for D is so if you consider as KA and this one is KB, so it's KA times the concentration of A and B, okay. Or in a different way, if you want to consider the K equilibrium, so KEQ is the product formation divided by concentration of A and concentration of B, okay. This one is rate formation, so it's not equilibrium of D, okay, so that one is wrong. Okay, so KEQ here is where KA comes into play, and once you rearrange this, so D, rate of D is equals to KA times A and B. Alright, so the above ones is inaccurate, almost there, but it's inaccurate representation. The second one is more accurate. Alright, so when you have this, okay, and you substitute A, B, and D into ES, and P. Alright, so it's just that instead of having just one reaction, you have two reactions in one equation. Alright, so when you consider this, the rate of change of enzyme over here is where you consider the formation of enzyme, okay, rate of change. So you have a formation and loss minus the loss, okay. So that's why if you consider the these all numbers that I mentioned, and K1, K2, K1 and K minus 1, alright, and we have over here K2 and K minus 2, right. So K2 is the ES forming the ENP, and K minus 2 is going into the opposite direction. So change of enzyme is all of these, the formation of the enzyme and the loss of the enzyme. So the rate is formation K minus 1, which is going backwards over here, okay, because from ES you are producing more E. K2 is where ES, again you are forming E, alright, and then the loss is K minus 1. Oh, K1, of course, yes, it's K1 because it's going from the E into ES. So now you are losing your free enzyme, and at the same time K minus 2, which is your free enzyme, again forming the ES complex. So these are the basic representation, mathematical representation of the change of enzyme concentration, okay. Similarly, you can do a change in substrate concentration, alright, so you can do it on your own. I'm not going to explain why anything and why the reaction is very short compared to the enzyme. Think about it, okay. And also you can have the change in enzyme substrate complex, okay. And finally, as I mentioned, the fourth one, you can have rate of change of products, okay. So these are four equations that you need to understand so that you can understand enzyme kinetics using the Michaelis-Menten model better. Alright, and I have here number one, because the Michaelis-Menten equation, the final ones at least, are combinations of a few steps. So the critical steps that you need to understand, or that you need to focus on, is the rate of change of products, because towards the end of the day, that is what you are interested in. Okay, now, so as I mentioned from the previous lecture, when you are talking about of product formation, you are less likely to say that the product can actually form the initial substrate. Okay, it can form, again, as I mentioned, it can form, but it's very, very unlikely. And if say the formation of a from a product to a substrate is very high, means that the reaction is not good at all, and you will scrap it away. So to have a good enzyme kinetics, what you want is the reaction is going only one way. Okay, so if that's the case, the K minus 2 that we shown previously is considered to be nullified. Alright, so that is where K2 is negligible. Alright, so again, in equilibrium, so the V, the rate of reaction is 0 because it's in equilibrium. Alright, so zero net reaction doesn't mean that it's not working at all, or the reaction doesn't work. It does work, but it's in equilibrium. Alright, so it might be a bit confusing for you. So if it does, just go back and listen to all these lectures especially about enzyme kinetics. Okay. Alright, so since it's in equilibrium, we can therefore study the rate of change at t equals to 0. Again, remember the slide that I mentioned initially, where you can have your Vmax, right? And you are interested in this V naught. Okay, so naught doesn't mean that it's at 0 second. It means that it's an early stage of the reaction. That's what we are interested in the early stage of reaction. So over here I abbreviated as t equals to 0, meaning that time equals to 0, but it doesn't mean that it's 0, 0. It means that the early rate of reaction, because to calculate the very early stage at t 0.00 second is almost impossible. Even if you are doing a reaction, it's almost impossible. So t equals to 0 means that you are trying to calculate the initial rate of reaction where it doesn't reach the Vmax at all. So you are trying to calculate the highest slope possible. Okay, so at this point there is very little product form. Okay, so that's the assumption that you're gonna make. Therefore K2 is negligible. Alright, so either product is not formed or product going back into the enzyme substrate complex is impossible, because with the end of the day we don't have EP. Alright, we have ES. So to convert the product to substrate straight away is not say it's impossible. Okay, it's always possible, but we for the sake of purpose of learning, we just consider it as negligible or very small. Okay, so if you remember reaction 1, which is the rate of formation from the previous slide, so therefore the V or V naught, since we are considering the t equals to 0, now turns into K2 times ES. Right, so the rate of formation is only depending on this. Right, so we are not looking at the K minus 2 anymore, because previously if you look at the reaction, it's actually showing to the there's a minus as well, right? So product formation, you have K2 moving forward and K minus 2 going backwards as lots of products, because of the assumptions that we put in and of interest. So V naught for product formation now becomes only K2 times the concentration of ES complex. Okay, and also assuming the steady state condition still applies. Okay, so there's no thermodynamic changes. The change of ES originally, where we have K1 ES, so again I'll just put it there, K1 K minus 1. Okay, so K1 times concentration of enzyme times concentration of substrate, which is a formation, plus K2 EP. So this is also a formation of the ES. Okay, but because we consider that as T0 and very less product formation, we take out that reaction, or we take out that representation. Alright, minus K1, K minus 1 plus K1 ES is the loss of, we're talking just about the ES. Alright, so the loss of the enzyme substrate complex. and therefore you'll get a new reaction, which is K1 times concentration of E to times concentration of S minus K minus 1 plus K2, that's the rate, or the rate constant times the concentration of ES at particular point, at that particular point. Okay, and when we arrange this, you get concentration of E times the concentration of S divided by concentration of E and S equals to the rate constant K minus 1 plus K2 over divided by K2, and this is where Km is written, or we call it as Michaelis constant. Alright, so the unit is mole per liter. Now you need to remember this because instead of just using this K minus 1 K2 representation, this can also be represented by just simply write down a big K and M. Alright. Okay, now the rate of change in P, therefore, so this is from originally from 1. Okay, so this is not the condition where we consider the equilibrium is only moving towards right hand side because of the assumptions that we made. Alright, so the assumptions meaning that at the initial rate of the reaction there is very less product formed, so therefore you consider it as negligible. Alright, so you take out that, and therefore you now only have V0 equals to K2 times the concentration of ES, and therefore when you rearrange this, oh wait, sorry, in from number 2, so number 2, which is the Michaelis constant down here. Okay, I did highlight number 2. You know that Km, okay, so just Km equals to E times S, concentration of E times concentration of S divided by concentration of ES. So what you do now is just simply mathematically rearranging it. Okay, rearrange, or to put it in more generic terms, is you times over right hand side over 1 over Km, and you do the same for on the left hand side 1 over Km. At the same time you times it by ES, and times over here by ES. So this is to make sure that the reaction is always it's always the same, right? So mathematically, that we're not going to focus on that. So what you want to know is that you rearrange equation number 2, which is the Michaelis constant, okay, to get ES equals to E times S over Km. Okay, right. So just remember on that. We'll stop there. Moving on to the other assumptions. So since its direction is at the beginning of the reaction, I'll just show you again. V0. Okay, so we are looking at the beginning of the reaction. So assumption is T equals to 0. So at that particular time, as I mentioned, in a biocatalysis reaction or in any catalyzed reaction, the catalyst is always smaller than the substrate. Okay, there's no point of having a lot more enzyme, the catalyst, but a very tiny substrate. Alright, so you consider that S is always higher than E. Maybe 10-fold, maybe 100-fold, but it's always in a greater excess. Alright, so when you consider total of S at any particular time, alright, so what you do is you have S total. So concentration of S total at any given time is initially the concentration of substrate which is free plus concentration of S where it's forming the ES, right? Okay, so this is how you calculate the concentration of S total in the reaction. Okay, but because the assumption that enzyme is always less, or in other ways, substrate concentration is way higher than the enzyme, you consider that, you assume that the product formation, the ES complex formation is very, very little at the initial point. So that's why from the original representation, overall representation like this, it is assumed that S total is just simply S free. Okay, so that's the assumption. S free, or the initial S, whatever you want to call it. So, or S0 if you want to call it that. Okay, so we are excluding the probability that there is an ENS complex formed. Okay, and at the same time, when you want to consider the E total, okay, you have E free plus ES complex. But this time around, you don't consider you do consider the ENS complex, because again, towards the end of the day, this assumption comes into play. Okay, and because the E total is very, very little, so you cannot assume that the ES complex is non-negligible, right? So E total is therefore considered as E free, or E plus the ENS complex. Alright, so when you rearrange this, you can get the E free equals to E total minus the ENS. Okay, I'm hoping that this one is more easy to understand, and this expression is we consider as expression number 3. Okay, and then what we do next is you put expression number 2 into expression number 1, you rearrange, then you will get this. Okay, hopefully you do get it. Alright, if go and have a practice on how you can actually get this expression. It should be fairly easy. You just need to do all the equation in very details that you can actually get this. Alright, so and you get that expression as number 4. So rate of change of product, okay, rate of change of product, or a V naught equals to K2, which is, if you don't remember, is the constant pushing forward to the product formation times E total times S. So S is also S total, but then towards the end of the day, because you consider S total and S naught is the same, so I'll just put it there as S. Okay, otherwise you can also put it there as S total, it's fine, but you know, it's the same thing, because S total equals to S, so you can just put it S, or you can just put S total, it's fine. Over the Michaelis constant Km plus the concentration of S again, so these two S's are the same. Okay, so when you consider the reaction number 4, which is the same as that one, you need to recall that the reaction will eventually reach a maximum velocity, right? So you will at one point reach Vmax. Okay, and this Vmax can be achieved when all the reactive site of the enzyme has now been occupied. Okay, so when all the enzyme has been occupied, so you don't have any free enzyme at all. You always have, well, you do have your free enzyme, but your free enzyme is always interacting with a new substrate. So it's kind of like the maximum saturation form that you that the enzyme can take place. Okay, so therefore what you can see is that E total equals to E free plus ENS. Okay, so because of the saturation, you no longer have a free E. Alright, so therefore you can consider E equals to 0. I know that you are actually producing E over here, okay, but this E will always goes back, so because the E is the same, right, the E is the same. So to get Vmax, when you reach Vmax, meaning that there's no free enzyme at all, the free enzyme is always interacting with the substrate. Okay, it's different when you consider the V naught, because V naught, imagine if you have a test tube and you have an enzyme in your hand. When you initially mix it, so at that particular 0.001 second, they are bound to be free enzymes. But now when you reach up here, when you reach Vmax, all the enzymes are already in the reaction mixture. So once the product have moved out from the active site, a new substrate will come in. So that's the assumption. Okay, so that's why you have the enzyme concentration to be S0. So therefore the expression now changes to E total equals to ES max. So you have a maximum of that. So you convert everything. So you convert all the free enzyme into an enzyme substrate complex. So you have your E total should be equal to your E of the concentration of your enzyme substrate complex. Okay, and therefore your Vmax, okay, imagine previously we looked at V naught equals to K2 times ES, correct? So now so Vmax, okay, so this one is V naught, therefore another expression is Vmax. It's simply just a substitution of V naught and Vmax, that's it. Alright, so now we are looking at two different locations. So over here at the top is Vmax, over down here is V naught, K2 equals to the enzyme substrate complex, and over here you have ES, also ES complexes, but now you know that you assume that at Vmax all the enzyme is already forming the enzyme substrate complex, therefore you consider that Vmax ES is now K2ES max. Okay, that assumption, and this we also represent it as K2E total. Alright, again, why? Because that's the assumption that we made. E total equals to ES max. It should be the same, right? Because the enzyme concentration can only be either in ES or in E total, because E total also includes ES. Okay, and when you rearrange this equation, then you will get E total, alright, over here, E total, concentration of E total equals to Vmax divided by K2, the rate constant. Okay, and when you substitute number 5 into number 4, what you will get is okay, so on the right hand side I have the equation for number 4 and number 5. Okay, so V naught blah blah blah. So when you substitute this E total into the equation number 4, where basically you are substituting that particular area, so what you will have is you have V naught. So now you can actually combine the Vmax and V naught. Alright, so that's very interesting about mathematics and how Michaelis-Menten derived this equation. So now we have V naught equals to the rate constant K2 times Vmax over K2 times the substrate concentration divided by the Michaelis rate, or sorry, Km is Michaelis constant plus the S, which is S concentration. Alright, so when you rearrange this, or you don't simply rearrange, so what basically this expression means is K2 times Vmax over K2 times S divided by Km plus S. Okay, so this is the expression. So when you have a mathematical expression like this in a straight form, as you recall, because they are the same, you can just cancel it out. Alright, so when you cancel it out, but of course you cannot cancel out the S, because the S is in bracket, right? So when you have a mathematical expression with a plus in the middle, so you need to consider that as one entity. So when you consider that, so you cannot simply cancel out the S's. So what is left is Vmax times S divided by open bracket Km plus S, which is the Michaelis-Menten equation. Okay, so there's a little bit of history in there, but I'm not gonna go into too deep. And what you can see now is the relationship between V naught, Vmax, and Km. Alright, so which is expressed here. So we have the same graph, rate of reaction, which is V. On the x-axis we have the substrate concentration, and when you plot the graph, you will have a Vmax at the very top, of course, and when you consider this one is a Vmax, and then this one is Vmax divided by 2, or half of the Vmax, the relationship is that the particular point about by which your Vmax is half, and you have your change of substrate product formation, the intersection between those two are actually your Km value. So this is where in the industrial application, if you are doing some enzyme kinetics, it's very important to know your Vmax, or even without knowing your Vmax, you can actually determine all the other values. Okay, so basically that is the basic for enzyme kinetics. In summary, MM, or Michaelis-Menten equation, can tell us the concentration of substrate which permits the enzyme to achieve half of a Vmax. Okay, so this is an optimization value. So as I mentioned, you don't want to reach Vmax, but by calculating Vmax, you can actually know the half of Vmax, or by calculating Km, you can always predict, because it's a mathematical expression, and at any given point you can actually know the other values, provided that you know some of the informations. Okay, and thus you can optimize the use of enzyme for your bioreactor and for your industrial application. Okay, so again, in summary, the assumptions that you need to make for all these to actually work, again, it is an assumption. So by knowing this, you can get a good or relatively accurate representation of your biokinetics or bioenzyme reaction. But you also need to take into consideration the assumption, which is number one, the steady state condition reaches that reaction very, very quickly. Because if it's a slow reaction whereby your E and S is very slow and doesn't form your ES complex, then the reaction will be very, very well, the mathematical expression now will be bad. Okay, so you need to have that assumption, thus creating equilibrium between the E plus S to ES in a very, very short time. Assumption number two is your catalytic process is the rate determining steps. Again, when you have that to produce E plus P, so you consider that as the rate determining steps. So you can have a very high K1 over K2. So if this happens, even in mathematical expression, you will say that K2 is the K catalytic, because it is the rate determining step of the product formation. Okay, so I wrote the binding step E plus S is fast, while ES to produce E plus P is slower. Okay, and third assumption is that at T0, or initial reaction, there is no or little product is formed. So P is 0 or negligible, therefore K minus 2. So the rate of moving backwards from the reverse direction for E plus P is also negligible, and you don't consider that as part of the equation. And finally, the fourth assumption is that at T equals to 0, the substrate concentration is way, way higher than the enzyme concentration, and that the enzyme substrate concentration at that particular time is almost negligible. Therefore, S total equals to S, but E total is always E free plus ES. Okay, so we will just stop here, because moving forward I probably need to stop in the middle of my talks. So today is the 4th, right? So I've already posted the first one. Now we have a total of 4 lectures, and we are following the original time point. Okay, and I think that's it. See you guys on Monday, but remember, on Monday and the next following weeks until week 12, we will have our asynchronous lecture, whereby everything will be in recording form, and for all intents and purposes, I didn't give you any code work, because you do not need to say that you attended this lecture. Alright, so only when we have a synchronous face-to-face lecture, even though it's online, that you need to key in your attendance, otherwise you don't need to. So I hope that you actually listen to this lecture and try and understand it. If you can't, watch it the second time. If you still can't, then you can always WhatsApp my email me. Okay, again, references, it's the same as during lecture 3. So additional materials that you can read and whatnot. Alright, and I think that's it. Thank you. Bye.